Welcome to the Global Membership Council webinar on energy system storage with focus on lithium-ion batteries. Thanks for everyone for attending. Right now we have approximately over 200 attendees. My name is Rock Meng. I'm your co-host along with Chief Mark Wasson. I'm a fire protection engineer based in DC, and I also serve on the Global Membership Council. Next slide, please. I have some housekeeping rules I want to go over really quickly, which have lots of information in this webinar I want to provide. Obviously, the webinar has been recorded and it will be made available on YouTube under ICC Media. The audience's members are muted with videos off by default. If you have a question, please use the Q&A function. And then we're going to leave the Q&A discussion at the very end. Next slide, please. So who we are, who's the Global Membership Council? ICOS, just for you guys who is not familiar with global membership, ICOS has been adopted in many other countries, including Latin American, Middle East, and Southeast Asian countries. The global membership connects co-professionals overseas, and we promote modern codes and building safety. And if you guys are interested, we offer additional webinars, and we have, education network opportunities. The web link will provide more information. This is actually our first webinar that the GMC collaborated with the Fire Service Membership Council. It is my pleasure to introduce my co-host, Chief Mark Wasson.
Thank you, Rock, and good day, everybody, and really appreciate you joining us. It's a great turnout. So, as Rock mentioned, I'm Mark Wasson. I'm an assistant fire chief and fire marshal for the Olathe, Kansas Fire Departments. And I'm here representing the Fire Service Membership Council Governing Committee. So a quick thank you to Rock for letting us join in and kind of co-host this webinar. I think everybody's in for a lot of great information today. So briefly on the Fire Service Membership Council, we're a forum for issues that are of interest to the fire service. And one of our big roles is that we help the ICC to increase participation from the fire service in the code development process. And many of you likely know it's heavy on the building code side of things, and we're always looking to try to get fire service folks more involved. So on top of that, we might advise the ICC on programs, policies, legislative matters, code adoption issues, and any other such matters in support of the fire service. So I'll mention that membership in our council is open to any member of the ICC, governmental voting members, or employees of a jurisdiction, corporate members, or ICC members of any closely aligned organization as approved by the board. So we'd be happy to have anyone join us that would like. We typically meet on the third Thursday of the month at 1:30 p.m. Eastern time. So if you'd like to join us, I believe there's information about our meetings on the ICC website, where you could reach out to any of our members. Be glad to have you. So with that, let's go to the next slide.
So we're very fortunate to have experts from the industry speak to us. I really appreciate their time and efforts. The webinar is actually divided into 4 topics, ranging from code development, risk analysis, state-of-art technologies, and fire department response. Each topic is really worthy of hours-long discussion. Obviously, we only have 90 minutes. So this will be an overview and basically focus on commercial applications. We are planning additional webinars for our overseas audiences. And we do want your feedback to see if there's additional interest, so we can plan additional webinars. Please, provide feedback in the Q&A section. Each of the speakers, their contact information are made available on the presentation. Please do feel free to contact them directly with courtesy and professionalism. Next, Chief Wasson will introduce our first speaker.
Yep, thank you, Rock. It's my pleasure to introduce Robert Davidson as our first presenter. Robert is the managing partner of Davidson Code Concepts. He has more than 35 years of experience in the fire service and over 25 years in code enforcement. He served on numerous ICC and NFPA committees and is a past chair of the ICC Fire Code Development Committee. He currently serves on the ICC Fire Code Action Committee, the NFPA 1 Fire Code Committee, and on the NFPA 855 Technical Committee for Energy Storage Systems. So very applicable to our talk today. Robert's going to present our first section on emerging fire technologies and adapting when technology development outpaces code development. So with that, Robert, I'll turn it over to you.
Good day. So what I'm going to do here is a quick history of where we are and where we are today with code and standards. I'm focusing on the ICC codes and NFPA codes, but there are other codes, globally that have historically regulated batteries. It's the use of the batteries that have changed. So though the electrical code picked up requirements consistently in many places, from a fire code, building code standpoint, the application started in 1997, where we carved out stationary lead acid battery systems. And really, we carved them out to eliminate treating them as a hazardous material installation because of the amount of electrolytes. We created a special place for them. In 2000, the legacy codes in the United States merged, and that language moved its way into the International Fire Code. In 2003, it moved its way into NFPA 1 Fire Code, and we added a new section, had to do with valve regulated. So we had a section on vented lead acid, a section on valve regulated, extremely similar. Next slide, please. So 2006 code, notice it's still stationary storage battery systems, primarily standby batteries, all right? They're waiting to be used. They're not being cycled as we do today with energy storage systems. We added lithium-ion batteries to the 2006 fire code based on the presentation, which point out they're low maintenance, virtually none, extremely safe, and the documentation provided to the committee claimed that they did not go into thermal runaway. We know that now that that's not the case. This is important for you to remember, because if you're on an older edition of the code that didn't catch up with energy storage system requirements, it didn't recognize the hazard, and what's in there is not adequate. We only required seismic smoke detection requirements. And NFPA 1 didn't make a code change at that time. We didn't always remember to address both fire codes in the same cycle. 2009, the fire code, both NFPA 1 and the 2009 code had changes. Still stationary storage battery systems. We added lithium metal polymer as a new technology, including thermal runaway protection. NFPA 1 added both lithium-ion and lithium metal polymer. And the International Building Code, which is the building code across the United States and many other parts of the world, changed how it treated incidental uses. And for the first time, you had a 10% limit of floor area. Battery installations were always an incidental use. And in older buildings, you'll find a whole floor level of them. But this changed it to limited 10% of floor area, which is actually a major change in the building code that a lot of people don't pick up. Next slide, please. So from 2012 to 2015, no significant changes. We're still treating them as stationary storage battery systems, primarily standby power. And then going into the 2018 code, the worlds had changed. The need for batteries, for sustainability, for support of grids, for distributed sustainability power, even including homes, was coming to be, and a recognition that the hazards were changing. And the type of batteries being used, lithium-ion batteries had taken off as the solution, providing the density at the appropriate cost at that time. So we extensively rewrote both the 2018 Fire Code IFC and an NFPA 1 Fire Code. Now they were known as electrical energy storage systems, recognizing that these are going to be cycled. They're not sitting in standby waiting. And that cycling, temperature changes, the hazard risks changes, and what can happen with a thermal runaway of a large system was recognized. As soon as the work got done on those two fire codes, NFPA had created the NFPA 855 energy storage system. Many of the people worked on the two fire codes joined additional people from industry on the NFPA 855. Looking at what was already in the fire codes, NFPA 855 was extensively rewritten and expanded, particularly because of the input of industry, giving us other areas where they would most likely be installed in, other hazards we had to address, places we could lower some protection levels. One of the things we did in the building code era is it's no longer an incidental use. In other words, we got it out of that portion of the building code and simply required 2-hour separation. That got rid of that 10% limit, but it formalized a 2-hour separation where in the past it was 1 hour, 2 hour, depending on occupancies. And the 2021 fire code got rewritten and pretty much matches similar to everything that's in the 2020 NFPA 855. Again, because we're trying to keep consistency. Next slide, please. So one of the key items of both NFPA 855, the International Fire Code, and NFPA 1 now uses extracts of that. And other documents I've seen globally is the construction documents, the amount of information that needs to be submitted up front. In the construction world, we like to do a lot of deferred submittals. But when it comes to energy storage systems, so many of the components relate on each other. The HMA, hazardous mitigation analysis, for example, looks at the whole installation. Well, you need all this documentation up front to do a thorough review to see if all the pieces match, that at the end, you're going to get a reasonably safe installation level. Next slide, please. So one of the key things to highlight is in that hazardous mitigation analysis, when they're looking at how everything relates, they may identify additional protection measures above and beyond what's already written into these standards. And those have to be installed appropriately in accordance with proper nationally recognized standards. And the other thing I'd like to point out here is, though in the IFC, we have a separate 1207, in NFPA, we have NFPA 855, which is extract NFPA 1. Sometimes we see in applications that come at the HGA level where I do work, where they don't recognize they have to comply with the whole code. In other words, you'll bring something up like, we're going to need fire hydrants and fire flows. Well, that's not in any NFPA 855. That's not in 1207. No, both fire codes typically have requirements for hydrants and fire flow, because the fire department needs water once they respond. So, the fact that you have to comply with NFPA 72 for the installed protection systems, you have to comply with all the details of NFPA 69 if you're doing a concentration reduction system, right? So there's a lot of other parts of the building codes, other reference standards that all come into play, and those documents are supposed to be coming in also. The large-scale fire test is critical to understand what size the event can be and what's going to be controlled in the event of a catastrophic failure. Both 855 and the fire code speak to large-scale fire tests, and there's an assumption, and it's recognizing that a publicly installed system should not go to a spontaneous thermal runaway. We also recognize that other things could occur to damage the system and cause that catastrophic. Okay, what are we going to have? What are we going to deal with? And more importantly, a portion of that test is, well, that one unit can burn up and not propagate to the end because we're not going to be able to put them out. One of the key things important to the fire certs, both in 855 and the International Fire Code, is fire mitigation personnel. In other words, these events are going to be long, right? Virtually burn out, then they have to cool down. And instead of the fire departments being tied up with their personnel at a scene, we require fire mitigation personnel be provided by the site to alleviate them, to provide for that. And these people have to have a higher level of knowledge. They have to have knowledge of what they need to do. Next slide, please. So, because of the history of codes, because everywhere in the United States, everywhere across the globe, codes and standards haven't been updated yet, there's sometimes people look at the codes like, well, we don't have requirements for that, so there's not much we can do. And that's not really factual in most places. Using the IBC here, it's an intent of the code that if we identify hazards, that we regulate them and provide for safety, particularly for firefighters, emergency responders. All right. And anybody tracking history right now knows that we've had 2 events that had serious repercussions for firefighters when a deflagration occurred. In one case, several were injured, sent to the hospital. In another case, there were some deaths. Next slide, please. So besides the building code, the fire codes goals are the same when it comes to fire and explosion. Next slide, please. So one of the key things that there's tools in the administrative portions of many different codes, whether it's NFPA, whether it's the ICC codes or other governing bodies codes, is that if the applicable standards requirements aren't in the code, if the requirements aren't there to address the hazard you've recognized, there's language that generally gives a code official the ability to go to other nationally recognized fire safety standards to show evidence of what to comply with. It's a tool for you to be able to reach out and address requirements. Next slide, please. So here again in the IFC and a similar language, building code and other documents I've looked at, if the requirements are such public safety and they're not in the code, they get provided. The code official decides what's going to apply. Now, where does this come into play? Somebody's on an older edition of a code. Maybe they're still on 2015 edition of the International Fire Code, for example. Maybe in their jurisdiction, the codes they're using haven't embraced the energy storage system topics yet. Well, you find that general provision that tells you, okay, well then that you have the authority to address it by looking at the more modern codes. You can look at the current codes and apply them through these sections to provide for the appropriate level of safety, right? And in the case of energy storage systems today with recycling, the issue is the previous language prior to 2018 didn't address that at all. So that language isn't appropriate. It is appropriate for you to use the current editions of the various codes and standards that are out there to apply to your situation. Next slide. So, the key is that we have a history of codes that are out there, and various jurisdictions on various editions of these codes that may or may not provide the answers, and along with all the work we've done so far to recognize the hazards of energy storage system as we know them today. And that work goes on in both code arenas. But Chapter 1, typically of the building codes, Chapter 1 of fire codes, whether it's the IFC or NFPA 1, they provide you that tool, that ability to grab newer standards and address that hazard as it should be. Next slide. Thank you.
Excellent presentation. Just for interesting fact that I believe most of jurisdictions are still under 15 or 18 I codes, especially here in DC, Maryland, and Virginia, where I am. Obviously, there's methods or tools that the HJ can adopt a later code. Next, our speaker is Dr. Francisco Jagler. Dr. Jagler is a senior consultant at Jensen Hughes with experience in the fields of fire risk assessment and fire modeling. Currently, Dr. Jagler is a member of the NFPA 550 and 551 committees, and he is also the chair of the working group developing the second edition of SIP Engineering Guidelines on Fire Risk Assessment. He is also the editor of the fire risk section of the upcoming revision of the SIP handbook. With my pleasure, Dr. Jagler, please.
Thank you, Rock. So and thank you for the opportunity to present. I'm going to build on what Robert just presented. He was talking at the end of his presentation of a hazard mitigation analysis that requires a lot of documentation that would be organized and presented in a comprehensive form to, in many cases, authority having jurisdiction. And that is the main topic of this presentation. there are requirements in the code for it. Some of the terminology can be confusing into what is actually required. And this agenda that I am presenting here is intended to go through what this hazard mitigation analysis is, and how we have been interpreting it, given the potential terms that are used in the codes that could make it confusing. So we're going to talk a little bit about risk assessment, a strategy to get it done for energy storage system, some available guidance, and then touch a bit on the hazards and mitigations, how we organize all that information in a comprehensive study. Next slide, please. So a very quick background. So these energy storage systems are growing in terms of use, right? They're showing up pretty much everywhere for many applications. And we are talking specifically here about energy storage. The lithium-ion batteries are used for other applications. And there is a key hazard to manage, okay? And this is the first topic that I'll just clarify in terms of how we are going to be using it. There can be failures in battery energy storage systems. There can be fires that are relatively small, etc. But the key hazard that can get out of control is thermal runaway, which it's a phenomena that occurs due to self-heating. And there are some known failure modes that we have identified and that we keep learning as some of these fires are studied. So it could lead to just local heating and pouch swelling in the battery cells or modules, or it could expand and propagate, and it could generate gases inside the unit or cabinet and have an explosive mix. And we all know some of the outcomes of such accidents. So the point here is that when we look at the requirements in the standard and how to put together this documentation, the HMA, it's practical to identify what can happen before thermal runaway, and when we talk about failure modes that can lead to those, and then the actual event of thermal runaway, and then we talk about the mitigations, right? So there are failures modes that could show up before thermal runaway. They induce thermal runaway. There are mitigation for those, and then if that fails and we do end up with thermal runaway, then there is mitigation for then try to control this event. So next slide, please. All right, so a hazard mitigation analysis, we hear the term HMA, and we hear the term FMEA, which is failure modes and effects analysis. So this is where I see sometimes some confusion. So FMEA is a reliability tool that manufacturers use and people in process safety use to identify failure modes of systems. In the context of fire safety, we have interpreted to be, let's identify what are the potential causes for a thermal runaway, right? So we limit the scope of an FMEA that could look for failure modes of system operation, what if the system fails, etc. But this doesn't lead to fire accidents. We kind of keep them out of the scope. So in summary, what it's included is failure modes that are known to generate a thermal runaway, and we keep learning about those. Cell abuse, physical abuse. There are some known failure modes associated with plating in the contacts, but it takes a simple Google search to find accidents that are reported publicly that are because there was a a fire outside the batteries and heat up the batteries, and that leads to thermal runaway. I have read events where there is a sprinkler system that leaks and water, it's a factor in thermal runaway. Some of these batteries have liquid cooling systems. Sometimes that leaks also. So there is a number of internal and external potential failure modes that we identify in these reports. So there is what we call the battery management system that monitors for the operation of these batteries in terms of charge and in terms of temperature. And that is perhaps, together with good housekeeping and following procedures, the main mitigation for preventing thermal runaway, which is monitoring these batteries, operating, keep the operation under the specified parameters, good housekeeping, etc. I should mention that I read in some of the codes a set of failure modes that should be considered in the HMA, which is the last set of bullets that we see here. And that is also, in my view, a source of confusion, because these are not necessarily failure modes of the batteries, right? What we see here, it's either reporting what to do if you have thermal runaway, right? Have a story for such an event. What if your energy management system, your battery management system fails? What are you going to do in those cases? If there are voltage surges in the system itself, that does not necessarily a failure mode of the battery, same as short circuits. What if your mitigation systems, instead of fire, smoke detection, gas detection, all of that fails, and dealing with spills? All of this does not necessarily refers to the battery. There is not failure modes of the battery. There's failure modes either of the battery, the system, or the system that you have in place in that location to deal with these events. And that's why I tend to think that this is a little bit confusing. The bottom line, regardless the terminology, if one comprehensively looks at all these points, you end up with a pretty thorough report, very consistent with what Robert was discussing, that you have to really understand how the system operates, how it's connected, how it trips under different types of alarms, etc., so that you have a comprehensive report. So regardless of how we call these terms, what we're talking about is internal failure modes to the batteries, external failure modes to the batteries. Then what do we do if we end up with a thermal runaway? What is going to be the mitigation in terms of fire for inside the cabinet, the storage system, and in the actual building or location where it's located, whatever applies, if it's indoor or outdoors, and then the response and how to deal with spills, etc. So it's a very comprehensive story that has to be developed and presented to the authority having jurisdiction. Next slide, please. All right. If you will look at this from the perspective of risk assessment, then every element that I mentioned of the hazard mitigation analysis will be important, right? Failure modes and hazard identification, that's part of the HMA. You have to list what can happen in terms of fire hazards. This case includes explosions. You have to have a very comprehensive list of mitigation, and that starts from housekeeping, fire prevention, right? The battery management system through the response to a fire or explosion. And then what are these consequences? And those vary really depending on where these batteries are located and the size of the battery. Indoors, outdoors, nearby communities, away from, all of that matters, and we need to understand. I will talk about this a little in a second, but Robert also mentioned the need for the testing, the UL testing. Well, that is a big source of information for us to develop, right, the potential consequences that are needed. So we structured this into an inventory. so that we see the chronology of the event, and in each step of that chronology of the event, we can identify what are the mitigations for the different events that can happen in the chronology, and what if those mitigations fail or they are not operating in time. Okay? And these results from the HMA, they inform pre-fire plans, they inform emergency response, you improve your procedures, you increase the facility oversight, and you can communicate risk. So they have a lot of benefits if you document this as required in the code. Next slide, please. So this is a list of the mitigations that we put as part of the chronology. So ideally, when you develop these studies, you're a developer of the study, if you're a reviewer, if you're the owner of the facility, you have to look at all the information available to the system. And I'm not talking about only the fire protection systems, the battery storage system as a whole, the one-line electricals, what kind of power it needs, all of that. And then by studying accidents that have happened, you develop the chronology and see what kind of mitigation you have. And some of this mitigation that is available may not be for thermal runaway. I mean, we have debates in the community, right, in the industry, of what kind of detection suppression is best for different types of fires that we can have. And some of them, or maybe there is a debate, not all of them, if not all, will actually stop thermal runaway. So you have to make sure that the HMA specifies the purpose of all the mitigation that you have. So I'll just summarize them quickly. We already talked about the management system to monitor the well-being of the battery. That is the key preventive measure for thermal runaway. Some of these cabinets are equipped with gas detection to monitor if there is hydrogen release and buildup and an explosive a mixture. And if that happens, we may start a ventilation system, explosion prevention, to vent the gases and just prevent the explosion itself. Then some of them are equipped with fire detection, and they would catch smoke and release, in some cases, a gas suppression. So you can now see logic involved. So if I didn't detect gas and I detect fire, I am going to release my gas and not use the ventilation system so I can hold the concentration, and vice versa. If I detected gas, I may lock the suppression system so that I can vent the system. All of that has to be well understood and documented. Some cabinets have explosion prevention and venting, deflagration venting. And then it's what are you going to be instructed your fire brigade or the fire department to do? The communication needs to be. So I have here a picture created by a company, Law, the manufacturer of battery systems. And this is the type of analysis that would be done if when one receives the testing results, the concentrations that were measured, to design these systems so to ensure, that we can vent, that we understand what will happen with these gases, and then all the mitigation, right? It has the best design possible. All right, next slide. The UL 9548 test data is necessary. It includes what they observe in the test, but also measurements of the gas concentrations that is used to support the modeling and the design of systems. I mentioned that. It's heavily referenced in the hazard mitigation analysis. It's used to support the design, right, of the deflagration venting and the ventilation, the explosion prevention. And basically it's key input to our performance-based mitigation design. So it highlights that what really the operator needs to collect when they are buying and installing these batteries. I already mentioned all the design information that is needed, plus all the performance associated with the batteries. Next slide, please. Part of the development of this HMA requires walkdowns. And although the HMA is not a code compliance evaluation, NFPA 855 or other applicable code have requirements that are good to look when you're doing the walkdown. For signage, for physical protection of the batteries, the housekeeping that is going to take place or is taking place if this is already built. Talk to operations about the sequence, right? There can be battery energy storage systems that have alarms due to the BMS, due to fire detection, gas detection. All of them gets reported through and to maybe even different groups of people within the company. Like if the battery management system is alarming, it may be some problem that is electrical, has nothing to do with fire. And you send a troubled person to inspect versus if you're detecting smoke, right? So all of that needs to be talked through with operations, with fire protection, with the fire marshal in the facility, and make sure that the HMA summarizes all that story consistent with the chronology of the event and the mitigations that are available. Next slide, please. We have seen that these sometimes get quantitative, and I'm not going to talk about quantitative risk assessment here, but there are HMAs that have required us to document a quantitative risk assessment. It's doable, and there are tools, and I reference our recent work for the SFPE in terms of the engineering guidelines, where we're trying to make this easy and efficient and effective for documentation such as the HMA, where you systematically go and say, this is the type of fire scenarios that I can have, these are the consequences, and then qualify the risk either qualitatively and quantitatively. And the only reason I'm mentioning this in this presentation is because in some HMAs, some clients request a detailed quantitative analysis. And when I say detailed, it doesn't mean, something that it's expensive, etc. It's that you have to quantify a level of risk for this client, and there are tools to do so. Next slide, please. I mentioned about an inventory and a chronology. This is a sample one that captures what we believe and have been doing, the essence of the HMA, which is not a brute force list of all the potential failure modes of the system, because this is a fire study, explosion study. So we look at what failures can end up in thermal runaway, and then what are the consequences, and we try to build a chronology of the event that starts with air sampling systems. Maybe we start the ventilation system. I'm going left to right in the chronology. Maybe we detect smoke. Maybe we have a clean agent system. Maybe we have water. Then we have a fire brigade or a fire department. And as these things become available or not, or they fail or not, or they actuate on time or not, you either succeed on the top branch or fail on the lower branch until you get to critical consequences. And these consequences are well defined in the risk literature for fire protection. In terms of negligible consequences are just, maybe an injury that is resolved with first aid, something that you would expect as part of your operation of the plant, of your facility, to something that goes beyond first aid, talks about serious injuries, serious burns, up to fatalities, and maybe up to environmental damage, right? So those would be the different level of consequences if we end up failing everything. And at the end, you can characterize very well what type of accident you can have, where are your mitigations, what would happen if they fail, and how likely that can be. And that gives confidence that you have basically covered comprehensively the entire cycle of operation, right? From a normal operation to some problems in the battery that the troubled person would address, to start seeing alarms that require a response and require planning with the fire brigade and fire department to, if it's let it burn, stay at a distance, then do them. I think that is the last slide. Thank you for your attention, and as we mentioned here, any questions we'll be happy to answer. Rock, back to you.
Oh, very good. So the hazard risk analysis is very critical. It's actually required both by IFC and NFPA 55. And basically make sure nothing is overlooked to minimize, any risks that could be arise. Risk assessment along with operations and maintenance documents are also required to be made accessible to emergency responders. I just want to mention that. Our next speaker is Rick Siddell. Rick is the regional sales manager for the Northeast USA region at Fike Corporation. Rick has over 24 years of experience in the fire protection industry, focusing on everything from clean agent suppression systems to combustible dust explosion and industrial fire hazards, and enjoys selecting and applying the best methods and technology to achieve the earliest possible detection and most efficient and effective means of extinguishing a fire event for any special hazards. Rick?
Yes, thank you, Rock. And again, my name is Rick Seidel. I'm with Fike Corporation, and I will just say I'm honored to have the opportunity to be a part of this panel and discussion today. So thank you. As we've heard from the previous speakers today, lithium-ion hazards are absolutely growing tremendously throughout the world, and they do present a truly unique hazard that to date has no one-size-fits-all or cookie-cutter approach or solution when it comes to fire protection. Fike Corporation, as a global manufacturer of advanced fire detection and special hazard suppression technologies, and my intent here today is to briefly overview some of the technologies that are proving effective on this specific hazard and provide some guidance on how to select the most appropriate approach when you have a lithium-ion energy storage system that requires attention. Next slide, please, Judy. There are many ways you can visualize or pictorialize the failure cycle of lithium-ion batteries, and I feel one effective way is by thinking of it as a clock or a round cycle, as failure to interrupt the cycle or stop the clock will result in a continuously growing hazard in both intensity and damage. Any form of abuse to any given cell will start the clock ticking from midnight, with thermal runaway occurring at about 5 o'clock. It's important to recognize that while we do have the opportunity to detect failures and pending hazards before thermal runaway, which I will refer to as the preventative zone, whereas once thermal runaway begins, we are squarely in a containment zone and have different options to consider. Next, please. The preventative zone is our window of time to detect and hopefully respond to and take measures to prevent an abused cell's clock from getting to thermal runaway. Detection of pending failure is achievable by precise monitoring of the surface temperature of the cell, or by detecting the off gas that is ejected by the cell during its initial buildup to thermal runaway, and subsequently integrating those signals with the battery management system, or BMS, to disconnect or isolate the affected cell or rack from the overall system or loop. Next, please. The containment zone is every second after thermal runaway has begun. There does not yet exist a system or extinguishant that is proven to suppress or stop thermal runaway once it has started. You can only take measures to try to contain it as best as possible to prevent further propagation amongst adjacent cells or surrounding combustibles. During thermal runaway, you will likely witness sparks and flame erupting from the runaway cells, which result in very intense and increasing radiating heat and smoke as adjacent cells much more quickly enter thermal runaway from the intensely propagating heat, thus presenting a spiraling hazard that can quickly get out of control and keep the clock spinning round and round. It's very important to try to stay out of the containment zone if at all possible. And the only way to do that is by making sure you have detection or monitoring in place to notice and recognize the sequence of events that will occur in the preventative zone. Next, please. One available preventative zone detection technique is thermal image monitoring. Thermal imaging has certainly come a long way in the past few years, and its applications are increasing and expanding to many realms of industry, manufacturing, and process monitoring. The software available for many thermal imaging devices allows for extremely customizable set points or alarm indications with the sensor's field of view to achieve very accurate and localized readings and reports. Thermal imaging can provide very early warning of developing hotspots or overheats so that your response protocols can begin as quickly as possible. Next, please. We can tie the thermal imaging system directly into the BMS to initiate rack or cell disconnect, but will not typically use a thermal image notification to activate an extinguishing system or to signal the building fire alarm, as a fire has not yet definitively occurred and we are trying to prevent it from occurring. One shortcoming of thermal imaging is that it is limited to line of sight from the sensor, and most energy storage system units are typically packed extremely full and tight of cells and racks, thus limiting the line of sight of any sensor. Next, please, Judy. Okay, advance one more, please. Thank you. Another available preventative zone technique is linear heat detection, utilizing new and advanced technology with fiber optic cable. Conventional linear heat detection cable relies on a given length of wire to melt at a determined temperature to signal that a thermal event is occurring. Fiber optic linear heat detection is a programmable and addressable linear heat detection system that can continuously monitor and measure the temperature along the entire length of the cable up to 6 miles and allows for different set points to be programmed in varying and or overlapping lengths of the cable. Fiber optic cable is extremely light and flexible and completely passive with no power or voltage traveling through it, which makes it a very effective solution in very challenging or rated environments. Next, please. Specific to energy storage system applications, you can monitor several units or containers with one system directly integrated with the BMS, and through the software, identify exactly where an upset condition has occurred. Alarm set points along the entire length of the cable are available and can be programmed as either a fixed threshold value, a rate of rise threshold, or deviation from average. These features make fiber optic linear heat detection a very viable means of localized monitoring in very tight areas or several areas next to each other, like these energy storage system containers typically end up at the site. Next, please. There's also a detection technique available that was developed specifically for lithium-ion battery hazards, and its specific goal was to detect the off gases they eject before reaching thermal runaway. The aptly named Lion Tamer product is an air sampling system that specifically looks for trace amounts of a unique blend of gases to offer very early warning signals prior to thermal runaway. Next, please. With constantly changing chemistries and technologies in the designs of lithium-ion batteries, it is very difficult, if not impossible, to nail down or focus on any one given gas. To be able to detect and signal a lithium-ion off-gas event, we must be able to detect a very trace amount of a blend of different gases, typically hydrogen, carbon monoxide, and carbon dioxide, but at very small amounts that a typical standalone single-point gas detector may not recognize or measure. Next, please. Judy, if you can please click on the video to see what an off-gas event looks like. And I'd ask everyone to focus on the upper right-hand side of the battery. I think it may have just went and we kind of missed it. If you can try to replay it there for us, look at the upper right of the battery. You see the battery jump just a little bit and some sparkles or sparks pop off the upper top right corner of the battery there. Those were the off gases being ejected from the casing of this lithium-ion, just AA size battery wrapped in heat trace, heated up to a point of failure to where that vent pops and ejects the off gases from the battery. That's the amount and trace amount of gases that could typically be ejected from a battery that the Lion Tamer system can pick up when properly calibrated and strategically located in the airflow of the battery. Next, please. In a typical energy storage system container application, this is what the off-gas detection system layout may look like. We'd have one monitoring sensor in each rack, again, strategically located downstream in the circulating airflow. We'd also have reference sensors provided to establish a continuously changing baseline of calibration within the system and all detectors so that the monitoring sensors can remain as sensitive as possible, but adjust on the fly, if you will, based on external contamination that may be present. For example, an idling truck parked outside whose exhaust is being drawn into the enclosure. The reference sensor would read that baseline, adjust the monitoring sensors appropriately to not unnecessarily set off every sensor in the room just because of that external influence. Next, please. Putting the battery failure timeline and preventative zone into a graphical representation, you can see that either of these techniques we discussed will give you a window of time to recognize an upset condition that may be underway, to be able to respond before thermal runaway officially takes hold or spirals out of control. Following the red line from left to right, you can clearly identify when the thermal runaway occurs by the sudden vertical spike. You can also see that there may be several minutes prior to that sudden vertical spike that preventative measures can be taken, and also that traditional smoke detection may already be too late, as traditional spot type smoke detectors likely will not sense anything until after that thermal runaway has already occurred or is in progress. Next, please. And specifically testing off-gas detection performance. The graph at the top of the screen shows an uninterrupted battery failure where off-gas was detected at approximately 32 minutes. The external heating continued and thermal runaway occurred about 5 minutes later. In the lower graph, upon detecting the off-gas, the battery management system was programmed to disconnect that cell from the circuit, and almost immediately from stopping the external surface heating, the surface temperature decreased and thermal runaway did not occur. Next, please. So we do know that it is possible to prevent thermal runaway, but we also must understand and be prepared for what happens if or when we do find ourselves in the containment zone. Most energy storage units do come equipped with some form of traditionally common fire protection approaches, being a typical spot type smoke detection and or a sprinkler head being most common. On occasion, they may come equipped with a clean agent fire suppression system. Unfortunately, by the time either of those systems are activated, the thermal runaway is likely already underway and well involved, and neither of those types of systems will stop or extinguish thermal runaway once it has started. In this case, they are only there to attempt to minimize the damage and protect the surroundings of the overall energy storage unit itself. Next, please. One such option that we may see on these units is a clean agent system. Clean extinguishing agent systems do remain extremely popular in many mission critical and high value asset areas, as they are extremely effective at quickly and cleanly putting and extinguishing class A, B, and C fires, and they're safe for occupiable areas at approved concentrations. But when it comes to discharging a clean agent system in an energy storage enclosure, it depends on when and how you plan to detect and discharge the type of system to determine its utmost effectiveness or level of protection. Next, please. Clean agent systems are, regardless of the clean agent systems that are utilized, they must be partnered with a pre-thermal runaway detection method to be the most effective. And the fiber optic linear heat detection system is the preferred and most effective type of system to activate a clean agent system. It will keep you ahead of the thermal runaway. It will not damage any unaffected servers, drives, or cells. And clean agents, one of their primary benefits is that they are safe to breathe for anyone nearby or who may be exposed to the gas. The amount of agent provided will be specific to the volume being protected. One of the disadvantages to clean agents is it does require the enclosure to be mostly airtight or have a high degree of room integrity, because agent loss through leakage, or the other variable to keep in mind is continued ventilation, will lower the duration and effectiveness of the system, as most of those systems are one-shot deals. And once that cylinder is empty and the room is flooded, there's no reserve supply unless it's designed as such. And again, if it's discharged after thermal runaway, the other item to keep in mind is that chemical agents can break down into additional flammable and or toxic gases at very high temperatures that are very easily achieved in a thermal runaway event of lithium-ion batteries, whereas inert gas systems will not. No agent will extinguish thermal runaway, another key item to keep in mind that we can't stress enough as we're going through this presentation. Next slide, please. Regardless of clean agent utilized, again, if it's discharged in the preventative zone, we will extinguish any non-lithium electrolyte fire and will provide a level of absorption and block radiating heat that may be coming from the event as it's escalating. But if it's discharged in the containment zone, it may initially extinguish the class A, B, or C combustibles, but the effectiveness for long-term fire protection is likely to be short-lived due to continued and evolved thermal runaway and leakage from the enclosure. Next, please. Water mist is another option and a relatively recently evolving approach, and one that is proving to be very effective. And water mist is defined and guided by NFPA 750, Standard on Water Mist Protection Systems. It defines a water mist approach as anytime you're using very fine water spray droplets less than 1,000 micron to extinguish a fire. Water mist primarily works by absorbing heat and very localized oxygen displacement at the transition point from where it turns from a solid droplet to a gas in the form of steam from transitioning from a solid to a gas. We can use water mist. It's very effective in class A, B, and C hazards. The benefits of water mist is that room integrity or the airtight of the enclosure is not as critical as it is with gaseous systems. And we can achieve a much longer duration of discharge with water mist than with gaseous systems. Most gaseous systems discharge for 10 seconds. Fixed water supply and pressurized cylinders, self-contained water mist systems, if you will, can typically provide 10 to 20 minutes duration and protection. And lower pressure, continuous water supply systems driven by a pump can potentially give you an unlimited duration of discharge into the hazard. Next, please. Water mist, if discharged in a preventative zone, same thing, will extinguish any non-lithium electrolyte fire and work to absorb and block the radiating heat. And if it's discharged in the containment zone, you can achieve an extended, continued, potentially unlimited discharge to provide a constant supply of water vapor to absorb and block the radiating heat as long as it is being generated. So very effective for long-term continuous protection. Next, please. So we've seen there are several different options and configurations and combinations from both detection and protection systems available. So the main question becomes, when do we do what? And that answer ultimately depends on what level of protection you need, desire, or require, and what is driving the need, and of course, to a larger extent, your customer or the owner's budget. Next, please. To summarize the detection options, we know that by thermal imaging, fiber optic linear heat detection, or off-gas detection keeps you in the preventative zone and offers the best chance and the most time to respond as quickly as possible to avoid a catastrophic event. Whereas detection in the containment zone, which is your traditional spot type smoke or heat detection and even air sampling smoke detection, or as well as flame detection or a sprinkler head to offer heat detection, basically just prompts you to respond as best as possible to try to help contain and protect the surroundings. Next, please. If we were to try to put these on a scale from good to better to best, you'll see that your traditional spot or smoke detection up at the top is good, but your linear heat detection and your off-gas detection is the best. Same thing from a suppression or protection standpoint. Having a level of explosion venting, which we haven't discussed here, but is a requirement for these units, offers you at least a level of protection. But obviously, when you get into the gaseous agent or the water mist systems partnered with one of those advanced detection mechanisms is clearly the best. And if I were to add another category at the very top of the arrow, being worst, to the left and right, you would find nothing. So doing nothing is the worst approach you can take. At least doing something is better than nothing, but you can clearly see that you can take some much better and much more proven approaches to give you the best level of protection. Next, please. This eye chart is my best interpretation I can make out of the questions and answers that NFPA 855 lays out to offer you guidance as to what to do when you have an energy storage system from a protection standpoint. You can see at the very top, number one requirement, regardless before any questions are asked, is you must have combustible gas detection to be able to provide an alert, and that is what the off-gas detection system can provide. From there are many yes/no type questions, and the AHJ's interpretation and requirements come into play based on where the unit is going to be located, generally classifying the energy storage system as being either indoors, outdoors, on a rooftop, in a parking garage, or being a mobile unit are some of the key indicators, and whether it's remote or nearby to other areas, that will drive you to ultimately what the codes will provide as guidance for the best level of protection for your unit. But they can, again, always be combined or integrated with one another to provide even higher levels of detection. Next, please. What seems to be the preferred or most accepted approach in the market with the full-scale testing that Fike Corporation has done with some ESS manufacturers, the obvious choice and the best preference and level of performance has been intelligent fiber linear heat detection cable partnered with a water mist system for suppression. Water mist has proven to be a suitable means of protection before and or after thermal runaway in absorbing the heat and trying to block the radiating heat and keep the temperature low on all surroundings as best as possible. Whereas the most code compliant protection system, if you followed NFPA 850 to the letter, you would probably have several combinations and several types of systems installed that may kind of overstep one another and make it much more complicated than it may need to be. But there are ways you can get to a very effective protection system by going through some of the practices that my previous colleagues have mentioned as well from a hazard analysis standpoint. Next, please. And just to kind of graphically depict here which detection and suppression technology is most appropriate or available, or where that puts you in the time frame as far as preventative versus containment zone in reference to thermal runaway. This slide here helps to show you. The important thing is just to know whichever selection you make, know where it puts you as far as your level of protection, and understand and be willing to accept that level of commitment. Next, please. I think that's it. I thank you all for your time, and thank my panel colleagues for the time and opportunity to be here with you today. Thank you.
Excellent. I just have a few comments. Obviously, sprinkler suppression is required for lithium-ion batteries. There's other alternatives such as clean agents. And the design criteria more often for clean agents, I don't think hasn't really catch up to the thermal runaway, all those other concerns. Number one, we need to have a really tight enclosure for clean agents to discharge. And there's a design concentration. Lastly, there's actually duration for clean agent, which is 10 minutes plus a safety factor. I mean, these are all of the above that must be considered. Obviously, if explosion that is a concern, oftentimes we provide ventilation. If the ventilation and clean agent discharge, these two events cannot happen at the same time. So I just want to bring that up for discussion purposes. Next, I'm going to have Chief Watson to introduce Chief Michael O'Brien.
Thank you, Rock. And boy, we've heard a lot of great information so far today on the code requirements, the risk assessment and hazard mitigation, and then finally on the detection and suppression. So thanks to all the speakers so far. The last piece we're going to talk about today is the fire department response to energy storage system emergencies. You don't have to look very far searching the webs or the news reports to find a fire involving energy storage of all different sizes. So please help me to welcome our final presenter. It's Fire Chief Michael O'Brien. Michael is the fire chief for the Brighton Area Fire Authority in Michigan and has more than 27 years of experience in the fire service. Chief O'Brien currently serves on the International Association of Fire Chiefs Board of Directors and represents our Fire and Life Safety section. Michael was a recipient of the ICC Excellent in Fire and Life Safety Award in 2021 and is also a past recipient of the Robert W. Gain Fire Prevention Leadership Award. He serves on numerous ICC committees, and he's the past chair of our Fire Code Action Committee. So with that, Chief O'Brien is going to present our final section on fire department response to energy storage systems and talk about the work that the collective community is doing to develop resources based on best practices. So Chief O'Brien, take it away.
Thanks, Rock, and a big thanks to all of our presenters today and everybody who's made it this far in the presentation. So I think you've heard that with energy storage, the fire service is being pressed now more than ever with a lot of variables and really something in trying to protect our our work environment where our firefighters need to go. Next slide. And if we pause for just a second and really look at some of the work that our firefighters are seeing on a regular basis, it's not just the finished product in an energy storage system or an e-bike or an EV, right? But we have this cycle of batteries that's occurring really around the world. And it's such an emerging technology. It's really been an interesting process to see how we've gotten to energy storage and supplementing our grid and providing power really when we need it. But I think as firefighters, we also understand that systems can have issues and there's multiple reasons for failure. But our firefighters are seeing fires really in all of these processes here within the cycle of batteries that we're seeing. Next slide. And really, if we put them into a couple buckets, right, we know that mobility has really risen to the top in emergency response. And I think the fire service is really just trying to understand what's happening in that arena. There's no doubt that electrical and hybrid vehicles are a portion, recycling, storage and manufacture, and of course, energy storage is all part of, right, similar chemistries, similar makeups, different types of cells, different testing parameters, different safety in all these levels. Next slide. And really the IAFC, the International Association of Fire Chiefs, came out. If you search IAFC batteries ESS, you'll get all of our resources that we've been putting together. And this is some of our membership in cooperation, not only with the work that we've done within the ICC or the NFPA process, but it's also working with critical partners to really get quality information out to the fire service. When we start to look at these simple response guides, we started with something in responding to electric vehicle fires. And then the request came, hey, how do we start to prepare for us responding to ESS? Let's go ahead to the next slide. So really with that focus, you heard today a lot of information about what the codes and standards are doing, but there's variables that I think we've never quite seen in the built environment. We've had a lot of black and white. And we've had a lot of certain things that we need to do. But really, the fire service has to be involved early in the design process. You heard some statements earlier about UL 9540 listing. That's probably one of the biggest things, is making sure that the units being installed in, and we're just focusing on commercial style installations, is making sure we're meeting those minimum code requirements, specifically UL 9540, but there are requirements for when we need to get into that large scale testing. And where it gets different for us in the fire service and this responding, we heard about the testing, the HMA, and all the things that take place really before we get a unit installed. But that foundation for how all of those are occurring is in this large scale fire testing, where we see how that unit responds. In each manufacturer, with their design team, with their protection measures, really start to elaborate how a unit is to take care of when a cell goes into an event or is starting into thermal runaway. And the hardest part probably for us in the fire service is you could have different manufacturers, you could have different locations with different strategies in the engineer and the design process. And so it's vital for when we start to shape what is our response, that we as the fire service understand the design implications, how the systems were intended to be utilized and used, and really what was within the design. Next slide. And so this bulletin that the IFC issued was really trying to help fire chiefs guide that conversation back home. And we know the importance of good quality codes and standards in utilizing up-to-date in getting our fire prevention folks well trained. Well, now what do we do with our ops? And so how we take it from that code environment and roll it into. And you'll see that for the most part, the manufacturers have an emergency response guide typically issued based on manufacturers. So we take that and we balance it with the use of the site-specific program. And really, most of the time, we're going to say, hey, look, we've got to allow that unit to burn itself out. And so this is a hard thing for us within the fire service because when we look at letting things burn out, that's not a typical approach for the fire service. But really, it's an optimization of probably resources when we start to look at it. And it's becoming exposure protection. One of the hardest things talking to a lot of fire chiefs that have responded to these incidents is, hey, what do we do for the time frame? And so we go from, a lot of fire department responses are handled in 30 minutes or less. And now we're talking multiple work periods with extended work times in very critical infrastructure. And so there's no doubt that our first approach is, hey, let's let this battery burn itself out, or the package to burn itself out. And applying water directly to the affected enclosure will not stop that process. Next slide. And so as we have to allow our crews to understand this, because firefighters are pretty smart characters, they're pretty good at trying to get their job done. And when we don't give them those parameters, it becomes difficult. So we got to give them some best practices. No matter what as we approach, I think when we look at fire department response to electrified areas, when we have ESS units that are part of utility grid support, we know what that looks like. We understand what that looks like. And I think the fire service knows not to go into some of those areas when it looks like utility support. But obviously installations aren't always in utility support. So key item number one is full personal protective equipment with SCBA. The smoke presents as much different and lazy. You saw in the previous slides that the characteristics of the smoke is much different than what maybe a lazy smoke might present as. Utilizing the pre-incident plan and getting on the phone with the specific emergency response group specific to that manufacturer. So I think the fire chief's demise is always trying to get their crews to have up-to-date pre-incident planning that's available at their fingertips. And ESS is critical. Where's the shutoffs? Where's the location? Where's our water supply? What resources have we agreed? Who's our emergency contact? And what can they tell us? You heard us talk about what the BMS, the battery management system, is doing. What can they tell you? And what I would say is when we have flames showing, our firefighters are very successful and they understand. The difficult ESS, just like a difficult building fire, is when we have light smoke showing in a unit. And that is a tough coordination. And this is why we're saying, hey, look, identify and get on the phone with the right person through your pre-incident planning. And there's some things that we've got to equip crews with. Hey, our thermal imaging cameras might not show adequate conditions because of how it's constructed. And today we're talking about lithium-ion, but what's going to happen as technology changes? There's a lot of funding going on around the world in creating the better battery, the safer battery. And so us as firefighters, right, we're talking about lithium-ion, but we've got to stay on top of technology. Next slide. So when we see something such as a venting ESS or energy storage system, we want to make sure we start to evacuate the area. So think about where these are being installed. Obviously, a commercial setting indoors is going to be very difficult versus utility grid on 50 acres, quite removed. And our response will need to be somewhat different. And we're going to kind of skip over residential units today, but really most of the manufacturers in their emergency response guides start to talk about what the safe distance is. And in that pre-incident plan, some of our work may be supporting something such as a remote fire department connection. It may be protecting exposure. And so really when we start to look at this, our job in the fire service is to say, hey, look, we need to match our response to the design that is going on. Most likely we're allowing this to burn out. Most likely we're doing some exposure protection, and this is going to be a long event. So, right, how do you rotate crews through? Do you have access to sufficient crews? Where's your fire protection water? And you start to think through all the parameters that it can take. These are complicated incidents. And oh, by the way, your current workload continues. Next slide. So as we start to talk through this defensive firefighting, really water spray is the preferred agent when we get into the fire response. If the fire's not developed and only smoke is visible, we go back to say, take that defensive stance. If you have hydrants or a rural water supply, secure it, lines in place, and we probably are going to be in a waiting game until we can get the experts on scene to aid our response crews. If a fire develops, take that defensive stance towards the burning unit and apply it to the neighboring. And in many cases, what we're seeing is that, hey, adequate safe distance is somewhere in excess of 300 feet. And you can, again, see one more time where we're going to say, hey, let this thing burn out. Next slide. And so how do we develop this patience during the response? Firefighters are innate, man. They want to go. They're hard charging. And in this case, we've got to take a breath to keep them safe, But B, this is really a case where engineering has taken a design solution. And we probably need to pause for a second because really our manufacturers, we've got a lot of great manufacturers doing the right things. They're developing cell technology that's robust, redundant, it can take the charge, it can take the demand. We've got battery manufacturers working to limit that fire to one cell, maybe a module, through technology, through designs. And if it doesn't last, we've got them hopefully limiting it to a container. And so I really have to, one of our biggest foundational pieces that we must keep pushing is how do we keep that fire small? And that's traditional fire prevention in so many ways. And so it's partnering and pushing with our prevention folks in that early design place. But developing that patience to understand that the systems are built in are just vital in our overall response. Let's go to the next page, and I'm going to show you real quick. Tesla has really worked hard to provide fingertips at or information at the fingertips of our responders. And again, this would be specific. If you have anything on the right-hand side, well, really anything in the commercial setting or anything on the right-hand side, your community and your fire service should have been intimately involved. This isn't just some quick training, right? This isn't just us rolling into town and saying, hey, look, you've got these new energy storage systems and we're going to train you for an hour. The fire department should have been involved well before. That's our manufacturers who are doing it right. They have the UL 9540 listing. They have achieved that through large-scale fire testing, and they're coming forward building that overall community fire protection structure. And so when you start to look at these products, they should have this introduction. But really, if you look at what we've got here, it's all the different levels that the fire service is starting to deal with. Emergencies, firefighting measures, how to shut down, first aid if necessary, right? You think about all the things we could interact with in an ESS system, from flooding to fires, coming into the enclosures versus coming out. And then really, how do we start to decommission? Next slide. And you'll see that just something as simple here within Tesla's, they've got great resources here in how do we respond to a venting Tesla product. They talk about their safe distance. They talk about defensive firefighting. They talk about personal protective equipment. And those resources are readily available. And each manufacturer, because there is so much in how they develop their protection strategy, Tesla, LG, and other manufacturers are not the same in what results they got in testing. And so really it's what has been engineered in and how do we go from there. And so I think for the most part, for us in the fire service, there's a lot of things being thrown at us, from foam, penetrating devices, other things. And really, our fire protection strategy, when we have large ESS in the commercial setting, should be developed well before those are installed. And then we should train to it. And 9 times out of 10, it's letting the unit burn out and it's protecting exposures. Next slide. Please, I encourage you all, head on out, check out the resources that the IFC. You can grab my contact information from the screen. I'd love to hear from you all. And really, right, how do we keep our firefighters safe? There's no doubt that safety for our firefighters happens well before the alarm, but it's making sure that we're doing great systems, we're following the codes and standards that so many of you are doing across the globe. And then it's how do we get the right tools to our firefighters so they're successful out in the field in something that they probably can't draw yet in their head because they haven't had that exposure. So, right, wearing the full PPE, defensive tactics, utilizing and getting the right agents. So thank you, and I'll turn it back over to the host. Thanks again.
Perfect. Chief O'Brien, first questions for you. We're going to the Q&A session right now, and we have about 11 minutes. So the first question is there any, I apologize, go back. So we are taking requests. There's lots of requests on the PDF copies of the presentation. I have already sent out some up to the 109 mark. And then if you guys do need presentations, please provide your email address. We'll make sure everybody gets a copy. I apologize. getting there. And then some of the questions has already been answered by our speakers. I'm trying to taking care of the one that.
Hey,
has
Rock,
been given to.
Rock, if it helps while you're looking, I'll read one real quick here while you're looking. Somebody says, hey, they got a battery manufacturers who's looking for direction from the FDA on requirements for 30% state of charge. And what I would tell Gareth there is the ICC committees developed some great proposals in battery storage for manufacturing. And they're available in the 2024. They're a little clunky to find. If you probably email myself or Bob, we'd be happy to hit you up on those. But really, the ICC family of codes, the ICC Fire Code, has a whole bunch of information on indoor battery storage. It's happening all around us. So happy to reach out.
Okay, here's a question, Chief O'Brien. How are fire departments scored in comparisons to fire brigades within the assessments for the mitigation plans? What training will be accessed for responders to rate their ability to handle the emergency?
Yeah, I think that's a good question. I think you're going to see a lot of changes coming up in the United States, probably with our standards for firefighters and batteries. I think earlier in the presentations when we heard the term fire brigades, I think some of us across the ponds and across the globe refer to their fire department as the fire brigade. So I think our firefighters, fire department, fire brigade, typically on big red fire trucks should be the same. As for industry specific, right, I think as we get more battery plants, as we get large ESS facilities, with people on site, right? It's again, I think like any fire brigade, they need to be properly trained, properly equipped to not only our community state standards, whatever those may be, but really they're going to be a vital part for us because we've been talking about that length of duration of incident. We've been talking about the need in some of these facilities are massive. They're acres upon acres. And so the right equipment, the right training, the right collaboration with the fire department, who probably has the statutory responsibility, is just vital.
Rock, this is Francisco for clarity, following up of what we just said. When I use the term fire brigade in my presentation, I was referring to an industrial fire brigade, part of a facility versus the fire department. And I was highlighting, if that is available, then coordination it's necessary. So just for a clarification on my slides, that's what I meant.
Thank you for the clarification. The next question is for Mr. Davison. Is there any movement in the codes to limit where consumer-grade mobility devices can be charged? Fire services is seeing lots of fires. Colleges are hotbeds for these hazards.
The answer is yes. Requirements for personal mobility devices, how to charge, where to charge, listings, listed charging was developed and will be in the 2024 IFC. But if anybody reaches out, we can provide that language to anybody who wants to be an early adopter of it.
Thank you. I think there's some questions that's already being answered. I want to just brought a couple up. Rick, can you address NFPA 18A, which is the suppression systems? Can you just comment on that, please?
Yeah, and I did not include them in my presentation simply because I am not aware of an engineered system solution specifically for ESS at this time using those agents. But I have seen video and I'm anxious to learn more about them because they do appear very effective in many realms. Perhaps I'd open that up to one of our AHJ officials here or the fire marshal officials to just see what their awareness or familiarity is with the additives per 18A and if they use them in any of their hose streams when they attack any of these fires.
So I've looked into this. This is Bob Davidson, and the 18A is it's an annex comment, right? The discussion, and it does mention BESS, but it points to NFPA 855, but it doesn't point out that both NFPA 855 and the International Fire Code specifically require large-scale fire testing of the specific technology and architecture for any suppressing agent to be acceptable under 855 or the International Fire Code. You know, and that's a key thing that we have to keep in mind as people throw solutions at us. Okay, but where is your large scale fire for that technology, that architecture that's actually going to work? I've only seen small scale tests for the encapsulator agencies. So that's where I'm at with it. Let's see the large scale tests.
All right, thank you. I'm trying to go through all the questions. Next question, I think Chief O'Brien already answered it. Any specific suggestions for response to ESS located in large residential buildings?
Yeah, and I think the key here is, right, again, we got to go back. Is it a properly listed system for the right residential? And when we look at where most of these units are going, again, we've got to very much be aggressive on ventilation and getting proper ventilation in the space. Most likely in our ESS, even in the residential, we can't stop the process. So it's very similar, it's just on a smaller nature. But you think about that attached two-story colonial with an ESS system. But the key here is if we can limit those from proper install, proper design, proper engineering from going into thermal runaway, that's the best.
Bob, do you want to comment on that?
I see a lot of
Yeah, so when we talk residential structures, we have separate requirements in both 855 and International Fire Code and the International Residential Code for detached 1 and 2 family dwellings and townhouses, right? And so, and the concepts of how we protect them are different. For detached 1 and 2 family homes and townhouses, we limit the size of the unit to 20 kilowatt hours. We require spacing, unless there's a large scale test document may be closer, so that if there is an event, it's limited to that single device. I mean, that's how we controlled it for the detached 1 and 2 family homes. If you're in a larger apartment building, condo, hotels, motels, etc., anything other than detached 1 and 2 family homes, townhouses, we prohibit them from being in dwelling units, and we require them to be installed the same as a commercial unit, which means if they're inside the building, they have to be suppressed on top of all the other protection measures.
Okay, another question. It's for you, Bob. I think the question is, let's see if I can find it. Let's keep talking. I think we still have a couple of minutes. Rick, do you want to talk about NFPA 13? And there's another question about 13R development.
I'm not all that familiar with 13 as we specialize in like 2001 and some of the special hazard codes. So I might defer that to someone else.
So
Okay.
this is Bob Davidson. We've with the sprinkler requirements, we didn't say install in a sprinkler environment, but all the model codes that are out there require even 1 and 2 family homes and dwellings to be sprinkled for new construction for quite some time now. All right. So when we add language to the codes, you know, there's assumption of buildings in compliance with the code. As far as any changes of 13 or 13D, NFPA 9540A has large scale testing, right? So there's the cell level, the module level, the unit level, then there's an installation level. The installation level is a sprinkler test. You put it in an enclosed room with sprinklers to identify if the density you plan to use is appropriate for that. As currently written, it doesn't include that for the residential units. And there's work that document's being in update now, and there's submittals to open that up, that somebody can go ahead and do that installation level testing to verify the density and also to validate that it'll provide a protection level. So that's where that's going right now.
Excellent. I think we still have a couple more questions, but I do want to close out our presentation. It's getting close to our 90 minutes mark. And I definitely want to thanks for each of the speakers for their knowledge and overwhelming responses. And then Judy, who is the VP for the Global Service Committee, she's behind the scene. I want to send a shout out to her. We are planning additional webinars. We do love to hear back from you guys. So let us know what topics you guys are interested, so we can provide additional education. Chief Watson.
No, I was just gonna echo the same. And please let us know where you'd like to see these go, and would encourage involvement with either the Global Membership Council or the Fire Service Membership Council, or both, if you would so choose. And just let us know where you'd like to see these, and hopefully we can continue to bring new and upcoming technologies and new challenges in front of you. So that's all I've got, Rob.
Excellent. All right. Thank you very much. And the questions that that hasn't been answered, I'm going to try to copy and paste and then send it to the speakers, and then we'll get back to you. All right. Thanks again. Take care.